Everyone, I'm Jiak Park, the lead developer of the ECMA project, and I also lead the Programming Language Research Group at Korea University. This video introduces our tools, Double Debugger and ECMA Visualizer. They are extensions of the ECMA toolchain that help users easily understand the official JavaScript language specification. You can use the Double Debugger by visiting this URL, and the ECMA Visualizer is a Chrome extension, so you can search for it on the Chrome Web Store or visit this link directly. First, let's have a closer look at our Double Debugger. Before using it, you need to wait until it has loaded for about 5 to 10 seconds. It depends on your environment. Now it is ready. The primary purpose of our debugger is to help users gain a step-by-step understanding of how a JavaScript program is executed according to the language specification. Our debugger consists of 4 main components. On top, there are buttons. You can control the debugger by pressing each button. On the left, there is a JavaScript editor. You can easily write any JavaScript point and program you are interested in. And the middle part is the spec viewer, which shows the current abstract algorithm of the specification. And the right part is a state viewer, which shows both program and specification state with 4 different tabs during the execution. Now for a detailed explanation, let's assume that I'm interested in this program and why this JavaScript program throws a type error by following the specification. We can start the debugger by pressing the run button and stop by quit button, and our debugger starts at the top level algorithm called run jobs. The middle part displays the algorithm names, parameters, and a link to the original algorithm in the specification and its body. You can follow the specification step by step using the step button like this, and like this. But however, the traversing entire program execution using only this button can take a long time. Thus, our debugger supports breakpoints. Let's search for the evaluation algorithm about additive expression. So like this, so we can add this evaluation algorithm as a breakpoint. And if you press the continue button like this, you can directly jump to this point. And the left side highlights the which JavaScript points are evaluated at this time. And you can see also call stack starting from run jobs. So here, and you can expand to see the tail or collapse. And also if you click each algorithm name, you can see the related part in the spec or the JavaScript pointer like this. So it comes from this function call during the evaluation of the function body. This additive expression is the current point. And the debugger also supports step over and step out buttons. Let's move on to the body of this algorithm. And using the step over, you can skip this another algorithm invocation like this. And also you can skip the remaining execution in the current function algorithm body using this out button. And also the step back over, back out button supports backward execution. It means that you can revert the execution using these buttons. For example, if you press the step back, you can go back to the previous step, or you can move using the back over to jump the inside the function algorithm, another algorithm, or you can go back to the call site using the back out like this. And also the rewind is the opposite concept of continue. So for example, at this point, if you press the rewind button, it goes back to the first breakpoint like this. In addition, the debugger also supports JavaScript level execution. Let's restart using the quit button and run button, and let's remove the breakpoint like this. Now using this JavaScript level execution, you can do like this. Using this JS tab button, you can execute each JavaScript part each JavaScript statement like this, and you can skip the function call using step over, and using the JS out button, you can skip the remaining part in the function body using JS out like this. Now let's try to understand why it throws a type error with the environment and heap information in the right side. Let's restart this debug execution, and let's add the breakpoint again for additive expression like this, and then let's go to the additive expression like this. And in environment, you can see the values of the variables in the specification level or JavaScript level. So for example, at this point, in the JavaScript level, we have the variables x and y. They are mutable variables, and their values are 1 and 2, because at this point it comes from this function call. 1 and 2 will be passed to the variable x and y. So at this point, the variable x and y have the value 1 and 2. And after evaluating this part, you can see that in the specification level, this evaluation algorithm returns this normal completion, and whose value is 3. It means that the result of 1 plus 2 is 3. And then let's continue. Then it stops again at this point, but from the different function call, from this JavaScript function call, again it stops at here. Now the variable x and y have different values, string ABC and an object. And you can inspect this object using this button in the heap viewer. In the heap viewer, you can see this object. It's the internal slot of this object, and its prototype is array, and this special internal slot represents the object properties. It has 3 different properties: length, 0 and 1, and their values are 2, null, and first matched with this array, because this array object will be passed to the y. And also you can utilize this provenance button to see where each record created during the execution. So let's see where this mutable binary record is created during the execution. So let's try to press this button to know that information. Then here we stop at the call site. During this function call, during the initialization of this function body, in this algorithm, it calls the create immutable method like this. In this algorithm, it creates the mutable binding for y. And then let's get back to the previous point using the continue button like this. In the same point, after evaluating this part, it also returns normal completion like this, and it returns string value abc, false. Now let's continue again. Now it also stops at the same point again, but with the finer function call here. But after evaluating this step, it returns not normal completion, it returns empty completion, more specifically throw completion. And you can see that this object, this prototype, its name is type error, so it means that it is an instance of type error object. So it returns type error during the execution of this algorithm. So let's go to understand the why, where the type error object created. So here, rewind this execution and then go to the body of this algorithm using the step button like this. And then now it takes left and right operand expressions and also plus as op text in step 1 to 4. After evaluating this in these steps, it evaluates the operands and the result is true and the begin to 2 and n. And the results are passed to the another algorithm with op text plus. And at this point, the L-val, R-val are true and to n, and op text is string plus. And op text is plus, so we need to evaluate the substeps of the first step. So in the substep A and B, it converts the L-val, R-val to the corresponding primitive values, but they are already primitive values, so there are no changes. And in the substep C, but there are not string, so it skips the step C and it reassigns the primitive values to L-val and R-val, but they are equal, but it means there is no change. And in step 3 and 4, it converts values to the corresponding numeric values like this. So true will be converted to the 1 and 2n is already numeric values, so there is no change. But in step 5, it checks the types of lnum numeric values, but here lnum is number value 1, but rnum is big int value to n, so their types are different, so it throws type error. So here it returns draw completion, exactly same object what we've seen in the previous process. So you can utilize double debugger like this. So that was all for the debugger. And now let's go to the ECMA Visualizer. Our visualizer is a Chrome extension that runs on top of the online language specification. So if you have successfully installed our ECMA Visualizer and enter the online language specification like this, you will notice an extra interface on the right side of the website. You can click this button to deactivate or activate our visualizer. To start our visualizer, you need to select a tab using the option and click. So option key plus click a specific step. You can see an example program like this. So it means that this program, during the execution, this program passes this step 5 in this algorithm. Beyond the example program, also a visualizer shows the corresponding the conformance test. The test 262 is the official conformance test suite, and the visualizer filters the conformance test past this step, the selected step. For example, these 5,672 test programs pass this step. And you can see the detailed test program by clicking this link like this. You can see the detailed test program, and also you can download each test program using this button, or download all the programs related to this selected tab using the download or button like this. And also users can also specify the call path before selecting a step as a context. For example, this algorithm has several references. Here, 10 different algorithms refer this algorithm. Let's go to the fourth reference. Here, the fourth reference is the evaluation algorithm for the subtraction expression. So this evaluation refers this algorithm. If you click this button, then we can go to this algorithm, and it automatically adds the call site as the call path as a context. It means that now we want to focus on this context. If you click the now if you click option click this step again, it shows different program because we have restricted context. It means that we want to see the programs pass this step through this call path. So this shows the subtraction expression, and it only shows the 137 test programs. And also you can add more call paths by clicking more like this, then it automatically added the previous call site as the call path like this, or you can clear the call path using this button like this. And however, and also another important is this one, because in addition you can see the programs or tasks related to this question mark operator. This operator is a shorthand for the return if mlopped operation. So this operator checks whether a given value is an mlopped completion and directly returns it if so. It represents exceptional cases. For example, if you select this operator with option click like this, it shows this program. It means that during the execution of this program, this algorithm applies string or numeric binary operator, returns mlopped completion. And also you can see 80 different test programs related to this edge cases related to this question mark operator. But however, only providing a program may not enough to understand the specification. So we support a direct link to execute an example program in the debugger by pressing this button. So if you click like this program like this, then you can see complex program like this and related to this edge case. Let's go to the double debugger to execute this program related to this part. So after clicking this button, it loads the double debugger and it activates another new button called resume. Using this button, you can resume the debugger to the selected part. So we selected this part. So if we press the resume button like this, it directly jumps to at this point. After evaluating this part, it returns the throw completion. And also you can utilize the provenance button here. It means that we want to see where this throw completion is created. So after pressing this button, you can see the call stack. During the execution of the primitive, it invokes the get method. So the input is the some object. So this object, and it tries to get the two primitive symbol. And so here at this get method, but the value of func is 0. So it is not callable. So it throws type error at this point. So you can understand why this program is related to the this edge case in this step 1b, and you can understand where the type error draws or is drawn in the specification. So that's all we have prepared. I hope this video helps you understand and use our tools. Thanks for watching.